So today we're going to talk about solutions and solution units, and this is really part 2 of a 3-part talk in which we talk about solutions and solubility. And today we're only going to focus on units that are used to commonly measure solutions because there's quite a variety that are used. So we're going to start by talking about dissolving sulfuric acid. And when it disassociates, you get, for every mole of sulfuric acid that dissolves, you get 2 moles of protons, which is what makes the acid, and 1 mole of sulfate. So one of the measures you might be interested in is molarity. And molarity measures how many moles of solute. Remember once again that solute is what's being dissolved in the solution, and solution is what does the dissolving. But molarity represents how many moles of solute are dissolved in 1 liter of solution total. So if I took 4 moles of sulfuric acid, dissolved it up to 1 liter, I would have 4 molar sulfuric acid, which means there's 4 moles of sulfuric acid in every liter of solution. It's a standard unit of concentration that represents the moles dispensed or present in a given volume. And the key here is that it's really the volume of the total solution that you know for sure. And another way to think about this is used for dispensing. So when you dispense a given volume, you really know the number of moles you brought into the reaction. It's also used in analytical chemistry. A lot of times if you have a colored solution or you have a metal or some material that can absorb light in the solution, you can figure out its concentration according to Beer's law, which says if you know the absorbance on an instrument, it equals the extinction coefficient, which is a property of the molecule, times the path length times concentration. And whenever you talk about concentration in Beer's law, you really are talking about molarity. It sounds very similar, but it's quite different. It's called Molality. And the difference is you see this small and usually italicized m, and it represents the amount or the moles of solute in the mass in kilograms of solvent. And if you were to do the calculation for water in particular, that also would be a liter of solvent again, because water has a density of 1 gram per mil. But there's a slight difference here. This isn't the total volume of solution, it's only the mass or volume of solvent added. So if I say I have 4 molal sulfuric acid, that means I have 4 mole of sulfuric acid plus 1 kilogram of water. So I don't actually know the final volume. It's 1 liter plus some because the sulfuric acid contributes some volume. And the important thing here with molality and why it's used, it really doesn't matter. You don't need to know the final volume. And if I look at 4 molal sulfuric acid, that also would have a total of 12 moles of ions in 1 kilogram of water, 12 molal in terms of ions. And that's because, once again, for every ion of sulfuric acid, every mole of sulfuric acid, 2 moles of protons and 2 moles of sulfate anion are dissolved in the water. So this unit of concentration is important for something we call colligative properties, which I discuss in the 1st and 3rd videos of this series. And it really has to do with the moles of pieces that are dissolved and the mass of solvent they are dissolved in. The volume of the total solution is uncertain and unneeded because what we're really concerned about is changing the properties of the solvent. So I need to know how much solvent is there. And then I need to also know how much is dissolved, and that's what this really tells you. These are commonly used in engineering applications where you're basically trying to raise the boiling point of a solvent, or maybe trying to lower the vapor pressure of the solvent, or you're trying to change the osmotic pressure of the solvent. Now I'm going to show you a couple demonstrations to help you differentiate molarity from molality. So what we want to talk about first off is about molarity, and this is a liquid concentration. So I have this 0.1 molar copper sulfate solution, which is really about 1 millimole for every 10 mils. And so the reason we might use molarity is we might want to control how much copper sulfate we're adding to a solution. Maybe we're interested in adding copper 2 ions to a solution. So here's my reaction, and it's ready to roll. So I want to control how much copper 2 I'm adding, and I want to add it by volume. So if I know that every 10 milliliters actually will provide 1 millimole, I can literally start adding it by volume. And if you'll look at this graduated cylinder, it's graduated in 10, 20, 30, 40, 50 milliliters. So as I start to add my copper sulfate, there's 10 mils. That's 1 millimole, 2 millimole, 3 millimole. So if I wanted to add exactly 5 millimoles of copper 2 plus to the reaction, I just add solution to the 50 mil mark. And away I go. And it's a lot more easy to do it this way than it is to use the scale and actually mass out the amount of material and then dissolve it. In addition, this copper sulfate is already dissolved, so it's fully disassociated, so it's very reactive, a lot of surface area. So that's one application of molarity. So what we want to talk about now is just about a different type of measurement. This is molality. And this is different in that we're really concerned about the total mass of the solvent and then how much solute you add to it. And the reason we're concerned about that is because it can change the physical properties of that solvent. So in this case, we actually just have water, and we're going to try and get it boiling here. I've got a digital thermometer on here, and I'm going to zoom in here so you can see what's going on. So what you have here is water, and there's some white material in there. Those are boil ethers. Those are just a little high surface area that prevents it from popping too much. And so we have pure water, and we're raising the temperature. We have a digital thermometer here. We are in Colorado, so we anticipate it'll boil a little early. So right now we're looking at about 88.5 degrees. So now the temperature is rising. All right, so now we have it to a fairly constant boil. If you'll look, the temperature now is about 94.2. There's very little change in the temperature. It's at altitude. We're at a mile above sea level, so we have a lower pressure here. But we have a fairly constant boiling point established. And so now this is 50 mils of water, and that's what we're really concerned about with colligative properties. So what we're going to do is we're going to take something that dissolves in water, which basically has a very high boiling point of about 200 degrees. This is glycerol. And we're just going to take about 20 mils of that. So that's significant to molality measures because it's the amount of solute. And all we care about then on the other side is the amount of solvent, which is 50. So we want to see how this amount of solute affects 50 mils of water. Okay, so now we have glycerol in water, and it's kind of established a new boiling point. It's fairly stable now. You can see that the temperature is fairly steady at 97.4. And so it's definitely raised, and that's a colligative property. Basically, the amount of material I dissolved is what's changed the boiling point. But as it goes to, in terms of solution, the calculations we do, we're not necessarily concerned about the final volume. That's not part of the solution. What we are concerned about was the amount of solute that you added to the amount of solvent. And the amount of solvent was 50 mils. The amount of solute we added, and we really would do the moles of that. So we could determine the moles of glycerol based on its volume and density, work backwards to the moles, and you could determine the molality. And the new molality is what determines the new boiling point. Normality is another measure. It's less commonly used, but I still want to show it to you because you'll see it from time to time. It's symbolized with a capital N. It talks about the equivalence or relevant moles of solute that's loose in the solution. So in this case, it depends what you're trying to do with the chemistry. For example, are you putting sulfuric acid in water to try and get protons free? If so, for every mole of sulfuric acid, you actually have 2 moles of protons. Or maybe you're actually just trying to get sulfate into the solution. Maybe you're using this sulfate to cast out barium ions, for example. In that case, for every mole of sulfuric acid you put in, you get a mole of sulfate ions free. And so equivalence or normality really kind of focuses on the important ions that you're after in solution, or the important pieces. So 4 molar sulfuric acid would be 4 normal in regards to sulfate ions because it's 1 to 1 molar. But it would be 8 normal in regards to proton ions, because for every mole of sulfuric acid you get 2 moles of protons. It is still used though in acid-based chemistry and electrochemistry. A very similar measure is sometimes called the equivalence per liter, or equivalence. And once again, as we said before, equivalence is just focusing on the most relevant ions. So really, equivalence and normality are very similar. So if you talked about 4 molar calcium sulfate in solution, you basically have 8 equivalents per liter in regards to calcium ions, and if you're talking about ionic charge. So for example, if you had an application where you're really concerned about the net positive charge created, each calcium generates 2 charge units. So in total, when you dissolve calcium sulfate and you had 4 moles of it for every liter, you basically would be releasing 8 equivalents in regards to positive charge. It's still used in medicine. You may talk about equivalents. If they're talking about ionic strength, or they're talking about charge in regards to osmotic pressure, or maybe even just the buildup of electrical energy from individual ions. Another important measure is where you compare the mass of solute to the mass of solution. And once again, this is the total solution, not just the amount of solvent you've added. So the units for part per mass could include percent mass divided by mass, which really is parts per 100, ppm, which represents parts per million, ppb, which represents parts per billion, and ppt, which represents parts per trillion. So for example, you talk about a chemical like acetaminophen. Of the carbon, hydrogen, nitrogen, oxygen that make this compound, 9.3 by mass of any acetaminophen mass is really occupied by nitrogen. And sometimes we use this for identification. These parts per million, billion, and trillion are quite often used in environmental work. For example, the Environmental Protection Agency will allow up to 10 parts per million of nitrate in drinking water. Anything above that would be regulated. And a pharmacy might carry 3% by mass hydrogen peroxide. So of the total mass of what you're dispensing, only 3% is really hydrogen peroxide. It's a unit of concentration that compares mass to the overall solvent. But once again, keep in mind the absolute volume is known. This is really for dispensing again. Parts by volume, very similar concept, but in this idea, you're basically trying to dispense a solution, 4 mils, 5 mils of solution, but you want to know how much of the important solute is being dispensed according to the amount of solution you dispense. So for example, if you have 70% isopropanol, like you would see in the drugstore at the grocery store, rubbing alcohol, that means of the total volume of 100 mils, for example, only 70 mils of that would be isopropanol. If I was to drink 100 mils of beer, 3.2 mils of that would actually be ethanol. And this is also often used to describe gases. So the air I'm breathing right now, of the 100 mils of air I breathe, I basically would only be taking in 20% of those mils would be from oxygen. So it compares volume to volume, and the important thing here is, once again, it's an application for dispensing. Sometimes there's an odd measure where you do mass per volume. In other words, if you dispense a certain volume, do you know how much mass of target reagent you're dispensing? And this still is used in the medical community. For example, if I say I've got a 0.9% sodium chloride solution, this is a normal saline solution that's used in IVs, then that means of every 100 mils that I dispense, 0.9% of that, or 0.9 grams, would be dispensed. And this is important because sometimes when you're dispensing chemicals, For medical reasons, it's done by mass to proportion it according to the mass of the body that you're trying to treat. So if you thought about an IV, you're probably set up so that you're dispensing so many mils per minute. So once again, this is used in medicine. This could occur with and this is an IV, intravenous needle attachment. So here's another concentration that's used fairly commonly in chemistry and in engineering practices. It's called mole fraction. And in this case, you're really concerned about a reagent. You want to know the moles of solute in the total moles that are present. For example, when you say it's a 4 mole percent methanol solution, that means of the total moles that are there in the solution, 4% of those are actually methanol. In regards to mole, this isn't in regards to mass, because remember, mass and moles are different. Mass is how much stuff. Moles is literally how many unique atoms there are. It's how many atoms. This unit is very important for doing partial pressures in chemistry. So if you're trying to figure out the gas above a headspace, and we'll talk about that in the third video, exactly how to put numbers on that. It's used for partial pressures, and it's also important to know that partial pressure, percent, volume per volume, and mole percent are all directly related for gases. And this is what Dalton figured out in Dalton's law. So let's get down to some actual calculations so we can see this applied. If I had 32 grams of calcium chloride and I dissolved it in 271 mils of water, the calcium chloride would occupy some volume. So when it all comes together and you take the final volume, it's 287 mils total. So apparently 16 mils is what 32 grams of calcium chloride would occupy. But when you find molarity, normality, molality, percent mass per volume, and the mole fraction, let's see how we use these numbers to find all these different measures. So starting with the beginning, molarity, I have to know the moles divided by the liters. So the first thing I have to do is turn grams of calcium chloride into moles of calcium chloride. I use the molecular weight. This came from off the table. 1 calcium, 2 chlorines, 110.98 grams per mole. That's going to cancel out my grams. It's going to leave me 0.288 moles of calcium chloride. Now, what volume of liters is my final solution? So now look at the two numbers that are given. I add 271 mils of water, but the final volume of the calcium chloride and water together is 287. So which one of these do I choose? Well, molarity wants to inform me as to how many calcium chlorides are distributed with a given volume. So I need to know the total volume of solution, not just the water I added. So in this particular case, I choose 287 mils. I convert it to liters because its molarity is in moles per liter. Final answer, there it is, the 3 significant figures, 1.00 molar calcium chloride solution. So now when I go to the next part, normality. Once again, normality refers to how many relevant ions. Are you talking calcium or are you talking chloride? So there's 2 different numbers here. If it's calcium, as you can see from the reaction here, for every calcium chloride dissolved, 1 mole of calcium chloride will yield 1 mole of calcium ions. So the molarity in this case is the normality as it pertains to calcium. But if you look at chlorine, for every calcium chloride that dissolves, you actually free up 2 chloride ions. So the normality as it pertains to chloride ions is 2 normal. Molality, once again, is the moles, which we've already figured out here. So that's how many moles of calcium chloride there is. And now I'm trying to decide, okay, what do I divide by for water? And in this particular application, we're not trying to figure out the distribution for total volume to do dispensing. We're talking about the total volume of water because we're going to change the properties of water. That's what molality is used for. So in this case, I really need to know the mass of water, the mass of solvent. And I describe it in kilograms. That's the standard units, moles per kilogram. Or 271 mils of water is 0.271 liters of water. Because the density of water is 1, that is also 0.271 kilograms of water. So I can put that into the calculation, and it's 1.06 molal calcium chloride solution. So that is going to reflect how that calcium chloride changes the properties of the water. And if you do the percent mass by mass, it's pretty straightforward. I just need to know the mass of the solute I'm adding, and then the total mass of everything involved. In this case, the water I added was 271 mils, which is 271 grams. Water is 1 gram per mil. It's unique. It's the only one that has a density of 1. And then you add it to the 32 grams of calcium chloride. You get 0.106. It's a unitless dimension, calcium chloride, but you usually describe that relative to if I had 100 units, so I multiply it through by 100 and get 10.6%. So if 100 grams of this particular solution, 10.6 grams of that would be calcium chloride. So that might help me for dispensing. And keep in mind, whenever you do percent, that is a parts per 100 unit. All right, so let's move on. We're going to do percent mass by volume, kind of the medical application. 32.0 grams of calcium. Get it to moles. We've already done that calculation if needed. That's for something farther down the road. Okay, 32 grams of calcium chloride divided by the 287. Now, in this case, we're once again talking about dispensing. This would be like a medical application. So now I need to know specifically the volume that this 32 grams was dissolved in. In that case, it's 287 mils. I do my calculation times 100, I get 11.1% mass per volume calcium chloride. So what does that mean? That means of every 100 mils that I dispense, 11.1 grams of calcium chloride were dispensed with that. And the last calculation here is finding the mole percent. So I've got 271 mils of water, but that is not relevant to this. I need to know moles of water. So I have to go to the periodic table. 2 hydrogens, 1 oxygen. That's 18.02 grams of water for every mole. I do that calculation. I actually have 15.04 moles of water. Now I'm ready to find the mole percent of calcium chloride. I know from earlier how many moles of calcium chloride I have. Now I got to find the total moles, which is the calcium chloride plus the water. And the mole percent is 0.0188. And this number is used in calculations in the third video. But a lot of times when you're expressing this, you use it as a percent. That's just commonly done. So convert back to the decimal for calculations. Convert to the percent for expressing the concentration. It's 1.88 mole percent calcium chloride. Of all the moles present, for every 100 moles, there's 1.88 of those are calcium chloride. But what might be important if you want to do partial pressure, for example, of water, is you would need to know the mole percent of water that's in there. And you'll see in the next video how knowing the mole percent can actually determine the partial pressure. So I take now the moles of water, divide it by the total moles. I get 0.981 or 98.1 mole percent. Or I could have taken this, if these are the only 2 components, and subtracted it from 100. So here's the second problem. 4 mils of ethanol. There's the chemical formula. It's 0.789 grams per mil. It's mixed with 96.0 mils of water. Okay, so what's the molarity? How much ethanol is distributed in the total volume? What's the molality? How does the amount of ethanol added affect the properties of that water, or vice versa? What's the percent volume per volume? In other words, if I'm dispensing this, how much ethanol do I get out with every mil of water that comes out? And then what's the mole percent of ethanol? Maybe you're going to do some sort of partial pressure calculation, and you want to know how by mixing these, it's altered the partial pressure that water generates or the partial pressure that ethanol generates. So first part, molarity, we have to know the moles of ethanol. And whenever you have a pure liquid and you have the volume, you have to have density in order to get to moles. So the density is given, it's 0.0789 grams per mil. I just put in significant figures here. Do the calculation. That would give me 0.316 grams. Now I can go to the atomic weight of 2 carbons, 4 hydrogens, 1 oxygen, and figure out it's 44.05 grams per mole. That means there's 7.17 e to the minus 3, 0.00717 moles of ethanol present, or 7.17 millimoles of ethanol present. So the molarity is you take the moles and divide it by the volume in liters total. Okay? So now pay attention what I do here. I have a certain amount of water, and I'm going to express it in liters, so I'm going to move the decimal over 3 times. So I have so many liters of water, and I have so many liters of ethanol. In total, that's going to be the total liters of solution. So it ends up being 71.7 times 10 to the minus 3 molar ethanol solution, or 71.7 millimolar ethanol solution. The molality, so once again how the ethanol might influence the boiling point of water, etc., etc. Now I need to know the moles of ethanol, but I divide it not by the total mass, but only the mass of the solvent, which in this case is water. Do that calculation. It's very close, but not exactly the same. 7.47 e to the minus 3 molal ethanol solution, or 7.47 millimolal. And now you can see why it's important to have that little italices in there, which still is hard to see sometimes. So now when you do the calculation per percent volume by volume, pretty straightforward. Mils of solute by total mils of in the solution. Move the decimal over twice, you get 4% volume per volume. For every mil, you're going to basically dispense 0.04 mils of ethanol, or for every 100 mils, you're going to dispense 4 mils. The mole fraction of ethanol in there, you need to know the moles of ethanol. Divide it by the total moles. Oh, but first we're going to have to find out the moles of water. In this case, there's 96 mils of water, which is 96 grams. Remember, density of water is 1. Divide it by the molecular weight from the table. You get 5.33 moles of water. So now you can take the moles of ethanol plus the moles of water. That'll give you total moles. The molar ratio is 3.83 mole percent ethanol. Or if I subtract that from 100, and there's only 2 components, it's 96.17 mole percent water. And that mole percent will influence the vapor pressure of the water vapor pressure. Or the water will influence the vapor pressure of ethanol in the headspace. If 8.9 milligrams of nitrate is found in every liter of sample pulled from a drinking water treatment plant, what is the concentration of nitrate in parts per million? So this is a good example to show you what goes on when people are doing parts per million calculations. The issue is that the 1 liter is mostly water and just a trace amount of nitrate on it. So how do we know the density of the total sample? At these concentrations, the 1 liter of water, really that mass and density swamps out any small amount of mass and change in density that the nitrate might contribute. And nitrate ions are over 2 grams per mil, but at this small concentration, that's insignificant. So consequently, 1 liter of water, 1.3, 1 times 10 to the 3rd mils is 1 times 10 to the 3rd grams. Okay, it's 1,000 grams. And if you do the conversion to milligrams, there's 1,000 milligrams per gram. So basically, you're talking about a liter of water has 1,000,000 milligrams of mass according to its density. And this is a convenient unit because you're basically looking for the parts per million. So that's really important to know. So if I just keep both of these units in milligrams, because I'm trying to do a kind of a mass comparison, I need to have them in the same units. I have 8.9 milligrams of nitrate ion, a million milligrams of water, so the parts per million are 8.9. And here's the real take home. Anything in milligrams per liter is really parts per million. And so you can keep working off that. A microgram per liter is part per billion, and a nanogram per liter is a part per trillion. So looking at this milligram to liter part per million approximation, maybe this makes you feel uncomfortable, but let's look at it this way. At 1,000 mils, you basically have 1,000 grams of water. You'd start to get a 1% error in this, this estimation that we're using if you had 10 grams of material or 10,000 milligrams dissolved. At this point, you really wouldn't be trying to describe things in part per million, right? When you're in that level of 10,000 milligrams per 1,000 mils, right? We've crossed over into doing percent mass per volume, percent mass per mass range. In other words, it would be more practical to describe it in parts per hundred or percent. In conclusion, it's really reasonable to work in a 0 to 250 parts per million range with this approximation. And just to kind of drive this point home, I pulled a section of the National Primary Drinking Regulations. These are the kind of contaminants that are regulated by the EPA. If you have more than these amounts in the water, and this is called the MCL, or the maximum contaminant level, and notice how it's measured in milligrams per liter or parts per million, and that 2 there is just a footnote, it's not a square sign. So if you took a material like hexachlorobenzene, it's regulated to 0.001 parts per million. So a long ways away from 250. In fact, on this section of table, and this is true of almost all the primary drinking regulations, the most concentrated one that you would look at is nitrate, the one we used in our example. And it has to be concentrations above 10 parts per million. So one last look at these units. Percent volume per volume is often used for acids. A lot of times you get a bottle of acid and they'll say 36% HCl, for example. That's concentrated HCl. So how do you turn that to molarity? Because that's a common thing that happens. You want to know the molarity if you know the percent volume per volume. So first off, use the definition of percent volume per volume to get the actual mils of HCl in a liter. So because we're going to molarity, we want to know moles per liter, so let's assume we have a liter of this material. If we had a liter of this material and we had 36% of that liter, right, or 360 milliliters of pure HCl, and here's what's nice. We already know from earlier that there's the density, and you need to know this number and the density together in order to solve this problem. 360 mils at 1.18 grams per mil, that's the density from. Then you go to HCl on the periodic table, 1 hydrogen and 1 chlorine, you get 36.46 grams per mole. You basically now know the number of moles in there. And this was done per liter, so you now have already expressed the moles per liter, 11.7 moles per liter, right? That's 11.7 molar. So a 36% HCl solution is really 11.7 molar HCl solution. So now that tells me if I'm trying to dispense it, that I'm actually dispensing 11.7 moles for every liter that I pour out, or 1.17 moles for every 100 mils that I poured out. So I hope this has helped you with solutions and understanding how to do calculations. In the next video on YouTube, we're going to really look into bigger applications.